Directed graphs. In the previous section, the edges of a graph were not assigned a direction. We could walk through them in both ways. As anyone with big city driving experience knows, this is not always the case in real life. That is, there are one-way streets too. A graph in which each edge is assigned a direction, such as in figure 9.5, is called a directed graph. It is natural to wonder under what conditions does a directed graph have a closed Eulerian walk. Of course, a walk in a directed graph must contain all edges in the right direction. That is, we can only walk through an edge from its head to its tail. Paths and closed walks are defined in an analogous way. Clearly, in this case, it is not enough to require that all vertices have an even number of edges adjacent to them. For example, if no edge starts in a given vertex, then there will be no Eulerian walk in that graph. In order to answer this question, we introduce some new definitions. We say that a directed graph G is strongly connected if for all vertices A and B of G there is a directed path from A to B. The in degree of a vertex of a directed graph is the number of edges that end at that vertex. The out degree of a vertex is the number of edges that start at that vertex. A directed graph H is called balanced if for each vertex V of H, the equality in degree of V is equals to out degree of V holds. Theorem 9.6. A directed graph G has a closed Eulerian walk if and only if it is balanced and strongly connected. First, proof. We prove that these conditions are necessary, as a closed Eulerian walk W leaves each vertex as many times as it enters that vertex. G must be balanced. Similarly, W provides a walk from any vertex to any vertex, so G is strongly connected. These two conditions are sufficient. To see this, copy the proof of Theorem 9.2, replacing edges by directed edges. A simple undirected graph is called a complete if there is an edge between every pair of distinct vertices. Thus, a complete graph on n vertices has n choose 2 edges. If we direct each edge of a complete graph, then the resulting directed graph is called a tournament. The reason for this name is the following. If n players participate in a round-robin tennis tournament, and we define a directed graph in which the vertices represent the players, and ij is an edge if I has eaten j, then we get a tournament. We have met tournaments before. Hamiltonian paths and cycles can be defined in a directed graph. 2. In the obvious way, while it is trivial that all complete undirected graphs have Hamiltonian paths, the corresponding statement for directed graphs is not that obvious. This is not surprising. While there's only one complete undirected graph on n vertices, there are many in some sense 2 to the n choose 2 tournaments. Nevertheless, they all have Hamiltonian paths. This is the content of the next theorem. Theorem 9.7, all tournaments have a Hamiltonian path. Proof. We prove the claim by induction on n, the number of vertices of our tournament T. If T has 1 or 2 vertices, then the statement is clearly true. Now assume that we know the statement for all tournaments having n-1 vertices. Let T be any tournament on n vertices. Separate any vertex V and call the remaining graph on n-1 vertices T prime. By the induction hypothesis, T prime has a Hamiltonian path H equals to h1, h2, h3 until hm minus 1. The question is how we can insert v into h. If there is an index I, so that v is an h, and the hi minus I plus 1 is an h, then we can insert v between hi and hi plus 1. If no such I exists, then there must exist an index k, so that k is between 0 and n minus 1, and for all j which is less than equals to k, vhj is an h, and for all j which is greater than k, hjv is an h. Therefore, either vh1 is an h, or hn minus 1v is an h. So we can affix v either to the front or to the end of h. What can we say about the existence of a Hamiltonian cycle in tournaments? Clearly, not all tournaments will contain them. For example, if T has a vertex that has in degree 0 or at degree 0, then T does not have a Hamiltonian cycle. It turns out that it is fairly easy to describe the tournaments that do have Hamiltonian cycles. Theorem 9.8. A tournament T has a Hamiltonian cycle if and only if it is strongly connected. Proof: if T has a Hamiltonian cycle, then that cycle provides a directed path from any vertex to any vertex, so G is strongly connected. Now assume that T is strongly connected and let E of T denote the set of edges of T. First, we prove that T does contain a cycle. Indeed, if it did not, then xy in E of T and yz in E of T, two edges in the edges of such a tournament, would imply that xz is in E of T, so T would be a transitive tournament. In such a tournament, the vertices can be listed from left to right, so that ij is in E of T if and only if j is on the right of I. However, such a tournament is not strongly connected as no paths go to the right, so T does have a cycle. Let C equals to y1, y2, y3 until yk be a cycle of a maximal length in T, and assume C is not a Hamiltonian cycle. As T is strongly connected, it contains an edge from C to some vertex x that is not in C. We can assume without loss of generality that this edge is y1x. If x, y2 were an edge, then y1x, y2, y3 until yk would be a cycle having more vertices than C. Therefore, y2x has to be an edge, and then similarly y3x, y4x until ykx must all be edges. Let Z be the set of all vertices Z, so that y1z is in E of T. Then yiz is in E of T for all little z in capital Z, and all I in k braces by the same argument as the one we applied for yix in the previous paragraph. Let zt be an h with little z in capital Z, and little t is not in capital Z. Such an h exists as T is strongly connected. Then little t is not in C, and therefore little t is not in Z, implies that ty1 is in E of T. Then, however, xzt, y1, y2, y3 until yk is a longer cycle than C. So figure 9.6 shows our construction. This contradiction completes the proof.